Okay, it's back. Okay. So, talked about what it means to be a function, what it means to be a one-to-one function. Now we're going to prove that if a function's inverse is also a function, then the function's one-to-one. And you're going to do this as an if and only if proof. I'm only going to prove it one direction here because I wasn't paying attention. So let f be a function such that its inverse is also a function. You with me so far? Okay. Let x and y be two elements in the domain of f such that their outputs are the same. How do you prove a function's one-to-one? You need to show that if the outputs are the same, then the inputs are the same. That's how you prove it. So, let x and y in the domain of f such that their outputs are the same. Now, since f inverse is a function, then anytime its inputs are the same, its outputs are the same. So since f inverse is a function, then f inverse of f of x is equal to f inverse of f of y. Since our inputs into this function were the same, then our outputs to this function have to be the same. What are the outputs to this function? X and y. So we showed that if f of x is equal to f of y, then x is equal to y. This is kind of a more abstract example. We'll do two concrete examples and then go over this one more time, and I think it'll make more sense. So let's prove that a very particular function is one-to-one. F of x equal to 3x plus 4. F is a function from the integers to the integers by f of x is equal to 3x plus 4. We're going to prove it's one-to-one. Let x and y be two elements in the domain Z such that their image is equal. We need to show that their image being equal implies that x and y are equal. We need to show this being true implies this is true. That's how you should prove an implication. Assume the antecedent, show that implies the conclusion, you're good. So, let x and y and z such that f of x is equal to f of y. What is f of x?
F of x is 3x plus 4.
3x plus 4. What's f of y?
3y plus 4.
3y plus 4. So if 3x plus 4 is equal to 3y plus 4, subtract 4 from both sides and divide both sides by 3, you get x is equal to y.
Yeah.
Therefore, f of x equaling f of y implies x is equal to y, so the function is one-to-one. That's what it means to be a one-to-one function. It means this being true implies this is true. That is the case. Make sense?
Yeah.
Let's do another concrete example. Let's prove that f of x equal to x squared isn't one-to-one. And we know that this function isn't one-to-one when we look at it, right? Because we have 2 goes to 4 and negative 2 goes to 4. So it can't be one-to-one.
Okay.
So we're going to prove it now. How are we going to prove it's not one-to-one? We need a counterexample. There's infinite counterexamples you could use. I just picked one. Observe that f of 2, what's f of 2?
4.
4 is equal to f of negative 2. What's f of negative 2?
4.
4.
So they're both equal to each other. So I found an x and a y, namely 2 and negative 2, such that f of x is equal to f of y, right? However, is x equal to y?
No.
No. So this function is not one-to-one. Make sense?
Yeah.
So now you've had some experience with it, let's come back and look at this one more time and make sure it makes sense. We're going to prove that, I didn't even prove it like that. If, here's what this one proves. If f inverse is a function, then f is one-to-one. So if f is a function such that its inverse is also a function, then the function is one-to-one. So let f be a function such that its inverse is also a function. Let x and y be two elements in the domain of f, whatever it is, such that they have the same image, right? I need to use the fact that f of x equals f of y to show that x equals y. So I know f of x equals f of y. Now, remember, f inverse is a function. What does it mean to be a function? It means if you give it the same inputs, it gives you the same outputs. So my inputs for f inverse are going to be f of x and f of y. I know that this is equal to this. I'm going to put them as both inputs into this function, which means what this function spits out has to be equal. So I plug in f of x to f inverse, and I plug in f of y to f inverse. Since f inverse is a function, if you give it equal inputs, its outputs are equal. But what is f inverse of f of x?
X.
What is the left-hand element paired with the right-hand element of x? Of the left-hand element x is just x. Similarly with y. Does that make sense?
Yeah.
Okay, so there's that proof. Next definition is OnetoOne. Let f be a function from a to b, then f is OnetoOne if and only if the image of f is all of b. Let me create a function really quick as an example for this. Yeah, OnetoOne. So let's do a is equal to the set 1, 2, 3, 4, and b is equal to the set 5, 6, 7, 8. So we'll do f is equal to 1 goes to 5, 2 goes to 6, 3 goes to 7, 4 goes to 6. Question, is f a function from a to b?
No.
It's not?
Oh, a function, yes it is.
Yeah, is f a function from a to b? Is that true?
Yes.
Yes, f maps everything in a to something in b. Is it a one-to-one function?
No.
No.
Or, that's not what we're talking about. Is it an OnetoOne function? It's not one-to-one, right? Because it maps 2 to 6 and 4 to 6, but that's not what we cared about. We meant OnetoOne. Is it an OnetoOne function?
No.
No, how do you know?
Does it map everything to be?
We don't use 8, right? The image of f is equal to 5, 6, 7, which is not equal to b. A function is OnetoOne if and only if the image of the function is all of b. So if f is a function from a to b, it's OnetoOne if and only if the image of the function is all of b. Does that make sense?
Okay.
So let's do a proof with an OnetoOne function. Let f be a function from the rationals to the rationals. What are the rationals?
Everything that can be put into a fraction.
All possible fractions. Any number that can be expressed as an integer over an integer. That's what we mean by rational. Is 7 a rational?
Yeah.
Yes.
7? How's that a fraction?
7 over 1.
Okay. Is 2.14 rational?
Yeah. Yeah.
That's a rational?
Yeah.
How?
It's 214.
It's 214 over 100. Right? Is 2.1414141414 repeating a rational? Yes, it is. How?
Never mind. Just kidding.
It was a joke? We'll show you how. Let x equal that, then 10x is equal to, no, 100x, let's go to 100x, is equal to 214.141414, whatever, repeating, right? So if we do 100x and we minus x from that, then that's going to 100x minus x. What do? We do this minus this.
You have to divide x.
What's 214 divided by 2? No, we're just going to minus x.
We can't minus x because we can't divide x.
Maybe we won't do that. Okay, now I'm just going to write over here 100x minus x is, what is it? 99x.
Oh.
Yeah. What was 100x though? 100x is 214.14 repeating, and x was 2.14 repeating. So what's 214.14 repeating minus 2.14 repeating?
212.
212. 212. So x is equal to 212 over 99.
Oh.
Easy as pie is what it is. Right? So yeah, that's still rational. We won't do any more about what the rationals are. We'll continue. So talk about a function from the rationals to the rationals. And we need to show that it's on 2. How do you show it's on 2? I need to show that for anything you pick in the image, anything you pick in this set, I can always find an x that maps to it. Right? That way everything in here gets used. How do I make sure everything in here gets used? I pick an arbitrary thing out of there and show how it gets used. Therefore, everything in there gets used. Does that make sense? So let's do that. So let y be anything in here. When we're taking y, we're taking it out of this set over here. They happen to be the same set, but keep track, this is coming out of this set. And I'm going to show how it always gets used, how there's always an x that maps to it. Observe that if I let x equal y minus 4 over 3, that's still a rational, right? If I take a rational and I subtract 4 from it and then I divide it by 3, is that still rational? Yeah. So if I have x equal to that mess, that's still a rational. And observe that, what is f of x? Well, that's f of this, which is equal to 3x plus 4. Let's see, I have y minus 4 divided by 3 and times 3. 3's go out. That just leaves me y minus 4 plus 4. That's equal to y. There you go. So for any y you pick, I found an x such that f of x equals y. So every y is used. Pick any rational number you want. 3. So Rhoda picks 3. So I'm saying let x equal 3 minus 1 is negative 1. Divided by 3. I'm saying let x equal negative 1/3. Then negative 1/3 times 3 is negative 1 plus 4 is 3. So it gets your number.
Wait, how do you get that, the right side of x? How do you get x equal to that?
How did I come up with this? Yeah, there's no reason that you should right now know how I came up with that. And I'll show you how you come up with an inverse function. I just want you to understand the proof first, and then I'll show you how to get that. So, how do you get an inverse function? If I have f of x, we'll assume it's from the rails to the rails like you're used to, is equal to, what do you want? 2x plus 1, something like that. Let's find the inverse of it. Well, first off, you're used to thinking about this as the right-hand element is equal to the left-hand element double plus 1. 2 of the left-hand element plus 1, that's the right-hand element, right?
Yeah.
Well, now we need to flip all our x's and y's. So x is equal, here, let me just do it for the exact one that we did. Since,
No, I think I know what you mean.
okay, so then x is equal to 2y plus 1, or in other words, y is equal to x minus 1 over 2.
Yeah.
So f inverse of x is equal to x minus 1 over 2.
Yeah.
This is the inverse function of this. This function undoes whatever this function does. Right? This function takes something, doubles it, and adds ones. This one subtracts ones and then halves it. It's its inverse function. So that's how I came up with this. Next definition is a bijection. What's a bijection? A bijection is a function that is both one-to-one and on-to. Make sense? So both properties, bi, to, bijection.
I have a question.
Go ahead.
Okay, so I was trying to think of a one-to-one function that isn't onto, and is that always the case when so like the function is a to b, b has to be bigger than a?
only with finite sets.
Okay. That makes sense.
Yeah.
Also, can you give me an example of an onto function that's not one-to-one?
An example of an onto function that's not one-to-one. So we have f from, an example of an onto function that's not one-to-one. So not one-to-one, we do f from R to
Oh, I see.
onto, not one-to-one.
Okay.
Right? It's onto. How do I know what this function is onto? What are all the values this function spits out? We already talked about this.
All of x was greater than 0.
All the numbers greater than or equal to 0. Right? That's what this is. So the image of this function is this, set. Oh, you guys probably aren't used to think about that set time intervals. That's more of a calculusy, but
Didn't we go over that in logic?
I don't know. It's either early in topology
I
or
don't
we
know
did it
why,
in
but
logic.
I recognize that. Do you recognize it?
Yeah, good.
I think that was chapter 0.
It was like
topology.
closed set and open set, or maybe it was in this class.
No, it was in topology, I think, when we were in chapter 0.
That's what I think it was. Okay, anyways. So, bijection. Bijection means it's both one-to-one and onto. Now let's do a quick proof with bijection. Proof. We're going to let A be the set of all evens and B be the set of all odds. Then f, the function from all the evens to all the odds by f of x is equal to x plus 1 is bijection, and we need to prove it. If we're going to prove it, we need to prove that it's one-to-one and onto. So, which one should we prove first? One-to-one? Okay, how do we prove that it's one-to-one?
We prove that two images are the same.
Let A be in, maybe we shouldn't use a B there, since B's what we call right-hand set. What should we call them? Let X, Y in A such that f of X is equal to f of Y.
Yeah.
And we need to use this to show that X is equal to Y. What is f of X?
X plus 1.
F of X is equal to X plus 1. Maybe we'll just write it this way. Then X plus 1 is equal to Y plus 1, right?
Yep.
Because f of X is equal to f of Y, which gives us X is equal to Y, which gives us 1-to-1. So we showed it's 1-to-1. Now we need to show that it's onto. We need to show that for any thing we pick out of B, we can find something in A such that f of A equals B. Right?
Okay.
So 3. Let little b in B. Grab something arbitrary out of little b. But if little b's in B, what do we know about little b?
Can be rewritten as 2c plus 1.
Yeah, it's odd. So if little b is in big B, what is big B? It's a set of all odds. So then there exists X in Z such that B is equal to 2x plus 1. Right?